simulation and correction of crystal distortions. So now it concerns more that part of the logo, more this part here, the visualization. So first, what we did? Set up a test, basically have a simulated image of the crystal, distorted that image, and then apply the CTF to it, and then either first correct the CTF and then afterwards correct for distortions, or in a one way, first correct for distortion and afterwards correct for the CTF. Basically to see if there's any difference in the quality of phases you get out of it. There was also basically just as a control, everything also without the CTF. So the question is, why do we do it? It's just from intuition. If you have the point spread function will stay. So this here is point spread function, 1 point is the defocus of the data structure. Basically, it's the back transformer of the CTF for deformers. And if you now do on this image, do some kind of distortion correction, be it an elastic one or a rigid one where it just shift blocks. What happens is you distort this point spread function, so it afterwards will not look the same as it was here. So if you do a CTF correction afterwards, don't exactly correct what you have. Sure, in real examples, the shift is not that big. That's just to show you the effect, what is happening. So intuitively, the correction of the CTF should be performed before you correct for crystal distortions. Yet normally it's done the other way around because it's easier. If you correct it in the end, you can just correct the extract amplitudes and phases. If you correct it before the distortion correction, you have to correct the full image. So the question was, does it really make a difference if you do it the other way around? So is there a gain if you perform the CTF correction first? And that's quite hard to answer if you don't have a proper simulation or if you work on experimental data. Because there you always have an uncertainty in your phases. And that's why we decided to do the whole thing on a simulation. Because if you simulate your crystal, you know exactly what the amplitudes and phases of your unit cell should be. So you can then also determine an accurate phase error. So now the question is, how do you do these simulations? So you have a protein crystal. Then you just assume that basically that's a unit cell. Okay, it's now near a monomer. In reality, it would be a tetramer of a necropore, but this doesn't matter, just to show you principles. And then we assume that you have for every unit cell, you have 3 degrees of freedom in the shift. And in addition, you have 3 degrees of freedom in the rotation. So that's the basis of the simulation. And really, for every unit cell, you can have an individual shift and the individual rotation. To be able to accurately simulate this distortion and then how you can correct for it. So, okay, again, you have three parameters for shift, 3 for rotation. The input used for the simulation is just a 3D density map of the unit cell. For this simulation, I basically just filled a part of the unit cell with noise, and also was running the simulation several times, every time regenerating unit cell, just to be sure that the phase error we calculate in the end is not depending on the unit cell itself, but just on the parameters. Okay. The projection of these individual unit cells is performed using an explicit Fourier summation algorithm. And for the simulation as it was running now, I used some restriction. One is we in a moment just shift in the x and y plane. Because basically, if you shift in the C plane, it doesn't make any difference for the projection as long as you don't apply the CTF. could basically do also Shift and C and then apply individual CTF for every individual unit cell. But I thought that's for the first simulation too complicated, so I restricted myself to XY plane. And also the rotation of the unit cell is only around the rotation axis perpendicular to the membrane plane. So basically what I'm simulating is distortion in 2D. I exclude for the moment the movements in 3D. Okay, so that's what it looks like. That's a projection of the reference unit cell. Then you apply an algorithm, and you see you get this image of this crystal which here you see it slightly distorted. Okay. The second part is renewed simulation of CTF and the correction. So I've chosen CTF including temporal and spatial envelope. And the simulation parameters are just taken from our CM2 effect, so it's a spherical aberration of 2 mm and a chromatic aberration also 2 mm. And also the CTF correction includes the spatial and temporal envelope. So basically the CTF should be fully corrected. Okay. Then the second part is once you have a simulated crystal, you need to search for the distortions in the crystal to get a map of vectors with your individual distortions to be able then to correct for that. And there we also have chosen a little bit a different way than what is done in MRC. Basically that's a schematic how the search pattern is in MRC. The MRC program is called quad search, so it basically goes from center. First searches all distortion in one quadrant, then the next quadrant, then the third one, then the fourth one. The search I implemented is a little bit different. It really goes growth from the center. The advantage of that is that wherever you are, you have to predict your current distortion to search for the cross-correlation peak. And here you have cases. If you here for the first quadrant, you don't have a lot of information once you're out here. And by changing the algorithm of how it grows, you just have more information to predict your individual distortion at every position you search for it. This gives somewhat an improvement that if the crystal is heavily distorted, it's easier to find the distortion, the actual peaks of the cross-correlation map. It means you don't need to iterate that much as you do normally with the quad solution. Okay. Then once you have done the distortion search, you need to correct your image. There I've chosen 3 different algorithms to compare them. Basically the one in the center is what is done that's wrong, that's not quad search, it's CC Unbending. What is done in CC Unbending, you basically just shift blocks. As a second one, I just implemented one which shifts the whole protein back, so the whole unit cell, but doesn't do any rotations. Just to see what's the effect of what error you get if you don't account for the rotations in a distorted crystal. And the third one I implemented is basically an elastic distortion one. I can quickly explain how I did that. That's you basically treat every individual unit cell individually. If you know from distortion search the 4 corner points of your unit cell, you can basically set up a set of bilinear equations, solve them, and then using these equations you can, for every pixel here, you can map the corresponding pixel in the undistorted unit cell. So this means this gives you really a different shift for every pixel in the image. Then once you know here, you have your pixels, you know the original position, you can here, if you're not directly on the pixel, but in between some of them, so you can do here just the interpolation and write back the grayscale value into the undistorted image. Okay, so now that's first result plot, was done last week, so it's quite preliminary. That's this plot here now compares the order of correction. So here you have the resolution. Basically, it's plotted 1 over the resolution squared. That's why it's not linear. It's just indicate your resolution. And here on the y-axis, you see the phase error. And that's for the original CT Unbending. So already here we use the original CT Unbending from the MRC. And if you first do the CTF correction, you get this kind of error. So it starts around 20 at 2.5 angstrom, you're 30. If you do it the other way around, you can see the phase error goes up to 50 degrees at 2.5 angstrom. So that's really, it makes a difference if you correct for the CTF first or you correct for CTF after the unbending.
So how much distortion did you apply?
That's this image.
And how much defocus?
8,000 angstrom. Yeah.
So what was the question?
Yeah, so it's hard to relate that to the scale of this. What did you assume the unit cell size is here?
Unit cell size is 100 angstrom. 100 angstrom, the extending is 1 angstrom. Yeah. So what I have to say is here, the absolute scale here of the error is really much, depends really much on the amount of distortion you have. That's the most crucial factor. So I tried with different kinds of distortions, and I always saw the same pattern, that if you correct the CTF first, you get a better result. But the absolute error you get varies quite dramatically depending on how big your distortion is. So for a very good crystal where you have very small distortion, probably both of them give quite a good result, because both of them have quite a small phase error. But the worse your crystal gets, the more important it is to really have the correct order, because you can here gain from the correct order of correction. Okay, that's the second plot that I just compares the different algorithms. As you can see, is the one just basically shifting the protein back without any rotation performs worst. That's what I expected, but I wanted just to try to see if it's really important to correct for the rotation blocker. What is quite astonishing is that actually the elastic correction performs better than the blockwise, because in a way, probably in reality, in physics, you cannot imagine that your protein is stretched, but neither can you imagine that it's just shifted in blocks. So, yeah.
But then you can. You have crystal defects and you have lens concussion distortions.
Yeah, okay. Yeah. If it's a distortion from the lens, then you could imagine that it's just an elastic distortion.
Yeah.
But if it's protein itself, it's hard to imagine. But nevertheless, it seems to be better. Yeah. That's what this was quite funny.
But is that on a real image or is that on your theoretical?
That's on the simulated image, because the problem is in the real image you cannot pinpoint your face for a perfect corrected case, so you can calculate the difference.
But when you do that on real proteins, you see a dramatic improvement with the elastic correction.
Yeah, that's now one of the next steps we want to take and really go and apply the different algorithms really on experimental images. That was just, you basically need a full project which is processed, and then do an average over several images and see if you get better resolution. Because that's in a way the only criteria you can judge and which algorithm is better. You cannot directly compare it on one image, because you never know which the phases you get out, which one is the correct one, which one is not. So, but that's definitely the thing we want to try. Yeah. And one thing is, one explanation I have for that is perhaps also that if you just have a rotated unit cell, if you use an elastic distortion, you can basically rotate it back. So it should get the full recovery of the rotation. That's just partially the case if you do a blockwise correction. Yeah. Mm-hmm.
So this seems somehow important for single particles, or I'm not quite sure. When we do electron crystallography, and you if you actually do it the conventional way and you calculate a Fourier transform of your on-band image, you don't really see much distortion in the CTF rings or any of this. And if you only phase flip, you basically just need to know whether your spot is on one or the other side of the zero transition.
I mean, just in here,
This is in real space, right?
that's in real space. So it's not just this the CTF you distort. You probably also change the amplitudes in the phases of the individual of your diffraction peaks. That's the point. That's really in real space. That's not the CTF. It's a post-wave function in real space.
Oh, I see, that's weird.
Yeah. But it's quite hard to judge how exactly you change the amplitudes in phases. That's why I simulated. But you for sure also change the amplitudes in phases of your diffraction peaks of your crystal.
So the two columns on the right would result in a dampened envelope function of the CTF if you do it that way wrongly, right?
Yes.
Yes.
Yeah.
No, that's too simple. Because the plots show that there's a change in the phase. I mean, the plots show, we know the perfect solution in the unit cell, and the envelope just is an amplitude correction, but we're talking here about a phase error. So there's something much more complicated going on than just the multiplication with a real number.
Because the high resolution components are shifted away from the center of the point image, and if you shift those, that's a phase shift of those higher frequency components.
Or you lose them. And that's an envelope.
But I don't think you're losing them here. I think you're just shifting them. So averaged over the whole crystal, you probably lose them more than you see the shift. Or at the edges of the blocks where you do the shift, you'll be shifting things.
Okay, so that's in a way the final message from the way it's implemented now to the optimal way to do the distortion correction. There's I think a considerable gain you can have. As I said before, it's probably for very good crystal it doesn't matter that much. But really, if you start processing bad crystals and want to get as much out of it as possible, then these things here start to be important. And we really now want to try to use that algorithm with the CTF correction before the distortion correction on a whole data set and see what will happen. If we can see really in the average, in the final merge projection, if we really see a difference. Then we can quantify it also in experimental data, not just in simulation.
Just here you would have the problem that you have to do the CTF correction on the current film image.
Yes. So it will be slower because you have to correct the full image.
Yeah, and then on a tilted sample will be
Yeah. Yeah, that is
reality.
that is anyway. That's it. That's somewhere in summary slide. That's now for untilted samples. It's easier. As soon as you tilt, it gets even more complicated.
Andreas,
Yeah.
would it be difficult for you to show the diffraction pattern of this bent crystal so that we have a feel for?
I haven't calculated that. They are impossible now. But theoretically, to do it,
No, but I mean,
Yeah.
it's usually so that we look first at the
Yeah.
diffraction pattern before we do all this unbending stuff, and
Yeah.
it would be quite instructive
Yeah, I could have done that. Yeah.
in terms of what you want to
Yeah.
show.
Yeah, that's true. Yeah, but unfortunately, don't have to.
I think the displacement you have shown here is not so dramatic. This is something which is sort of what we see quite often.
Yeah.
I mean, what was the sort of maximum shift you had? If you look at the vector field,
It's about a unit cell.
Yeah, it's already quite a bit.
yeah, or half
So-
a unit cell or something
Okay,
like
so it's
that.
on the order of a unit cell in this 20 or 30 unit cells across.
Yeah.
So I'd say that's a lot of distortion.
Right,
It's
so
completely
it's for
the
band
resolution
crystals,
is-
this is what he said, but I mean, we should sort of get a good feel how close that is to reality we are dealing with.
Yeah.
I mean, if we have...
Yeah. I mean, there's one option which you can also do, which I plan to do, but it's just didn't have time yet now, is basically take an artificial unit cell that I know the amplitude in phase, and then apply a real distortion vector map from an experimental image. I mean, you can determine these, say them, just load them in here and use this real distortion, and then simulate it again. Just didn't have time to do that. But that's definitely also a thing I want to do. Then I probably can tell more about the magnitude here. But I use different distortion, I mean the small distortion, the trend is the same. So there is a difference in the order. The magnitude, that's really, this depends on the distortion you have.
Andreas, one other
Yeah.
thing, it looks like your unit cells are well separated. I mean, the asymmetric unit is, and therefore the PSF, the most important part, is actually localized and not really interfering with the neighboring ones. So actually making a simulated crystal that actually has crystal contacts where they're actually,
Make it work.
Yeah.
yeah.
Yeah, probably then the effect would be worse. But I mean, even here, to go back to this one here, that's point spread function at 8,000 ohms for defocus. And I think it used here a little bit smaller unit cell, but it extends quite far. So even here in the simulated case, the point spread function will extend beyond the unit cell. Not that much, but for sure, if you have a more packed unit cell, probably the effect will be worse. So there's a second thing I thought of. But this came to my mind when we were working on a project of out-membrane pouring. That perhaps this distortion is not really 2D. I mean, you showed it also that crystals are not flat, and also in your group, Philip is working on that, doing some particle analysis. And so I just thought, okay, let's take an experimental distortion map. Just for every unit cell you have, you get a set of unit cell vectors, and you know the original unit cells. So basically for every unit cell, you can directly from this, using Scholl's algorithm, calculate the tilt angle and assemble a map where you show the tilt angles depending on the units. That's what I did for this project. It's a KDGM crystal. As you can see here, that's just the crystal indices. And this here, what I have to say is this here's the tilt. So you really see this crystal seems in kind of ripples.
What is the tilt? What is the maximum tilt defined?
It's around 10 degrees.
And what's the maximum difference in tilt between neighboring unit cells?
This I didn't calculate, but I could, could have looked at it.
The crystal growth defects are now calculated as tilt.
Yes, that's the problem. I mean, here you have the assumption that it's a defect in the crystal, or you assume that it's tilted. You cannot do both, at least not with one image. People in Madrid went into that direction. If you take the crystal and the crystal image at 2 different tilt angles, then you can identify both. Then you have enough data. But just from one projection, you cannot distinguish. So, in fact, this here might be a mix of distorted crystal defects and tilt. But it's just funny that you really that this tilt is in kind of ripples. I think probably here the crystal is not flat. There might be additional effects. I mean, you also see here, you have these weird holes and things. There might be some defects which then give these weird tilt angles. But for sure, the crystal was not flat. So that's also the future direction we want to go. Basically, now with the simulation I have, you can also simulate these kind of crystals. because you can have a shift and you can have rotation in every direction. So you could actually start and simulate these kind of crystals and see just how does diffraction pattern, the Fourier transform look, and what kind of distortion maps you get out of that. Then perhaps also better understand the experimental distortion maps we have to see if this is perhaps more tilt than distortion in the unit cell. Yeah. Okay, so that's really my last slide. Conclusions. I think it would be important to correct for the CTF and for the distortion correction. I mean, in the best case you gain something, if crystal is good, it doesn't matter. So it's a little bit more intensive in terms of computing power. So you lose a little bit of time, but that's it. The quality of the data should improve. Different distortion algorithms have different performance and different limits. So we saw, for example, if you just shift back the unit, so that's one limit. This probably works well as long as the crystal is not, don't have any rotated unit cells. As soon as it's the case, it breaks down. Okay, the third thing is that's what you already mentioned. As soon as you have a tilted sample, you have gradient defocus. This very much complicates the distortion search and the correction. Because there you also have to take into account that if you have a reference and if you don't correct for the CTF before you do the distortion correction, the reference will have a certain defocus, so the cross correlation will be better in parts of the image than in other parts. So, yeah, that's a complicated topic. Oscar will talk a bit more about how the CTF, the contrast behaves in samples. And the third thing is, crystal distortions are probably not only a 2D phenomenon. Therefore, we should also start exploring really strategies to account for the third dimension, like unit with the maximum likelihood approach, and maybe do like kind of some particle, or that you determine distortion mixtures in 3D or something like that. Okay, finally, I'd like to thank the people who helped here. Andreas Schenk gave me the opportunity to work in the lab, and here, the three guys who are on Scott, Valerio and Marco, we stand together to the method development faculty, and Andreas Signorel, Mohamed Jami, and Hervé Remichi. That was actually their project with KDGM, where I took the images from and did the unbending stuff to test it on this instrumental images. Okay.
One important question. Is there any merit in, particularly in the unbent untilted samples, to just picking out the individual single particle images using the cross correlation peaks, classifying the images classifying the images, and then trying to determine what tilt angle is of those various classes, so that you could put the tilt angles back in to do the correction later?
I think that's, you probably can answer better. That's basically what Philip did in on David's lab. Right.
Yes. So tests have been made on simulated crystals and also on matching crystals in secondary transport and metabolic terminals to analyze the distortions in the take that into account in using CTF.
As I understand it, like you're looking at the classification, you're looking at the angular shift, and I wanted to just get a sense of whether one method is more reliable than the other.
This is too early. I think we need to move on, because otherwise Ansgar has not